Um, Hi, everyone. Very glad to be here and present our research work, an investigation of Byzantine threats in multi-robot system. My name is Ge Lei. Currently, I'm a PhD student at Nanyang Technological University, Singapore, under the supervision of Prof. Zhang Tianwei, who should be presenting just now. So we are a research team from Nanyang Technological University and Institute of Computing Technology, Chinese Academy of Science. And today I want to talk about the Byzantine threats in multi-robot systems. MRS has been widely adopted in real-life scenarios. We have seen a lot of examples in industrial usage, like assembly, exploration, mapping, etc. And recently, those applications are extended to our daily lives. There are many service robot teams, rescue robots for all kinds of emergencies, and we also have swarm robots. For example, if you have seen the Tokyo Olympics opening ceremony this year, you must have seen the drone swarm team performance. So all these applications raise us to care about the security of the robotic systems. The past research works mainly focus on single robot, including both the attack and defense. To summarize, a single robot can be vulnerable to multiple types of attacks, which allow the adversary to fully control the robot. The primary reason is that the robot operating system, the mainstream library for robot operation and communication, contains many loopholes. It lacks the basic security mechanisms, and also the function packages contain the known vulnerabilities. Moreover, the ROS platform is open source, which allows everyone to upload and share their function packages. But there's no source code review process. So the adversary can actually upload a malicious package that contains a backdoor or a piece of code that allow the adversary to take control of the robots that use these function packages. As a result, we need to think about the scenario where the adversary may exploit one robot in the system and further attack the whole system. We model this problem as a Byzantine threat problem, and our scope is focusing on the mobile multi-robot system with one Byzantine robot. The following figure demonstrates a good example. In the navigation system, 3 robots are working together to visit a series of waypoints predefined by the ground control station. So these paths are calculated by the station based on the status of the 3 robots. However, if one robot is malicious, it can send the false information to the station. And as a result, the path for the other 2 robots will also be changed. So we can see in this example, the adversary robot actually doesn't have any physical interaction with the other robots or the ground control station, but it can influence the overall system behavior just through the messages communicated with other robots or the station. So we consider this as a very typical example of how a Byzantine robot can attack the system. And we want to analyze these kind of attacks in any given multi-robot system. So in this work, we only focus on one Byzantine robot within the MRS, but our methodology can also be extended to systems with more vulnerable robots. So with this in mind, here is an overview of our proposed methodology. We firstly developed a requirement-driven funding methodology to study the Byzantine threats in different MRS. We then built an MRS workload suite, which incorporates the standard implementation of common MRS workloads and coordination schemes. So finally, we select 5 different workloads. After that, we identify the threats in the selected workloads and verify them through simulation and experiments. So here is an overview of our methodology. It contains three components: a requirement specification generation module, a data flow analysis module, and a requirement-driven fuzzing module. So the first module is actually to study the MRS workload and generate the requirement configurations, which defines what are the rules for the system. The second part, the data flow analysis module, study the workload and understand how the Byzantine robot can communicate with other components within the system. The third part, the requirement-driven fuzzing module, take the output from the previous two parts and run the whole workload in the simulator to identify if a Byzantine robot can compromise the system with a certain mutation message. So in the next step, I will explain the three modules in details. The first part is the requirement specification module, where we use the signal temporal logic with the robustness semantics to describe the requirements of an MRS. We consider both the general requirements, which means that those requirements are applicable to all kinds of multi-robot systems, and some task-specific requirements for different workloads. For instance, in the navigation workload, we consider the percentage of waypoints visited. For the exploration workloads, we consider the map generation accuracy. So combining these two parts together, we can measure the current system performance and how close is it to a predefined system failure. So in this way, we can tell if a system is closer to the system failure or far away from system failure. Secondly, we have the data flow analysis module. In raw system, robots are always communicating in a publisher-subscriber mode. So we can use a data flow graph to represent the nodes and the messages communicated between them. We extract the cross-robot Byzantine messages by analyzing this graph, because we focus on how the Byzantine robot can communicate with other parts of the system, like other robots or communication or the ground control station, and use these messages to take over the whole system. So then we have the requirement-driven fuzzing module, and the pseudocode of this part is listed on the right side, the figure, and it actually contains 4 steps. Firstly, we will mutate the message. To do this, we study the common message types in multiple systems, and we manually customize the mutation strategy for all the message types. For instance, for the sensor measure of the distance, we can increase the data measure or decrease the data measure. What we try to do here is to simulate how the Byzantine robot can change the message value to affect the system performance. We then have the simulation and requirement checking part, where we run the workload in the simulator and we monitor the system with the requirements. So we check the system failures and requirements violations to directly see if a message can cause the system failure. If there's no system failure, we will calculate the current system robustness, which is how close the system to a possible failure state. And we can identify the robustness changes resulted by the mutation message. So we can record the result and use this result to guide the next message mutation. For example, if a mutation message caused the decrease of robustness of the whole system, in the next round, we will mutate the message in the same direction so that we're closer, or we are possibly closer to a failure system state. Our study object is an MRS workload suite. To summarize this workload suite, we study the past MRS works. We summarize those works from different perspectives, including applications like navigation, exploration, rescue, etc., and also different coordination schemes centralized, decentralized, mixed scheme. We then do some generalization. A very good example would be box pushing and navigation. The box pushing task is to let the robots to move a series of objects from one position to another. But after some analyzation, we realized that the only difference between the box pushing task and the navigation task is that in box pushing task, the robots are carrying something. So basically, fundamentally speaking, those two workloads are very similar. So in the end, we select 5 typical workloads, which we think that can cover different cases and usage scenarios of all the MRS workloads that we can see in the common cases. We have the centralized coordination scheme with the navigation workload and the exploration workload. We have a decentralized scheme with 2 exploration workloads based on different map merging strategy. And we have a formation workload, which is based on the swarm robots. So the details of these workloads can be seen from in our research paper. And you can also check them because we have already open sourced these workloads. So we then launched the proposed methodology over the 5 workloads, and we identified 3 types of attacks, or what we call the threats within the system. We summarize them as attack 1, task assignment control attack. Number 2, merging poisoning attack. Number 3, task forwarding manipulation attack. In the next section, I will briefly talk about these attacks and their consequences in the different workloads. So number 1 is the task assignment control attack. Well, in multi-robot system, the final goal is usually decomposed into many small subtasks so that the system overall gain is maximized. For instance, here we have a multi-robot system exploration task where 3 robots are given the task to explore this region. You can see the routes of the 3 robots, and they have very little overlaps because in this case, the overall system performance is optimized. However, a malicious robot can actually use the false messages to compromise the task assignment decision process. For example, using a fake location, fake status, or fake message baiting information. So, for example, a robot can pretend it's to be very close to the region to explore by sending a fake location message. So the final task will be assigned to this robot, although actually it can be very far away from that region. In this way, the system performance is downgraded. The second type of attack is map merging poisoning attack. In the exploration tasks, the final map is generated by merging the maps from all the robots. But unfortunately, after examining the map merging packages available online, we noticed that those packages does not verify the correctness of the map data. As a result, the proposed method identifies that the easiest way to pollute a map is to simply introduce a fully occupied map data to the final result. So the whole map is poisoned. And actually, all these map merging packages cannot detect this kind of attacks, which may cause very serious issues when the adversary robot present in an exploration task. The third attack is the task forwarding manipulation attack. In some systems, especially the swarm system, it is assumed that there's no centralized controller and the task is given to one robot. Then this robot will broadcast the task information to the surrounding robots. And in the end, the system is synchronized. So a Byzantine robot can easily manipulate the task information in case of no detection or prevention mechanisms. The attack outcome is very different from a single robot failure case where one robot is not functioning. Let's see the following example. Originally, we want to let the robots to form a line. This is the normal case. And in case that one robot is idle, or in our case, not functioning at all, we can see that the other robots can still form a line based on the relative positions to the other robots. And they try to form a line to cross this idle robot so that the final result is still correct. But in case that the adversary robot launched the attack, it can easily introduce another task into the system, for example, to aggregate and form a circle. This can result in very different workload execution outcome, and the attack is successful. So we evaluate the consequences of those different attacks in the simulation and real-world experiments. And for different workloads, we have different metrics. For navigation, we measure the completion time and navigation success rate. For exploration, we measure completion time and the map quality. For formation, we measure the formation similarity, where we define as the structural similarity between the ideal structure and the final formed structure. And the attack outcomes are mainly two types, where firstly, the system performance can be downgraded, or secondly, the task can be fully failure, then the workload cannot be successfully executed. So different attacks have different impacts in different systems. Here we give some key takeaways for your information. So generally speaking, centralized systems are more vulnerable to map poisoning attacks because the map generation is fully based on one centralized controller, and there is no failure resilient mechanisms. On the contrary, in the distributed systems, the robots can aggregate their maps in a more false resilient way, and the attack will cause the outcomes that is not as serious as what happened in the centralized systems. Well, on the other hand, the centralized systems are more vulnerable to task assignment control attacks because the task assignment process highly relies on the messages from each robot. And in this case, robots cannot verify the messages from other robots since the system is decentralized. So the adversary can easily use some false message to take control of the whole process, which significantly downgrade the system performance. Task forwarding manipulation attacks can have very serious consequences without any prevention mechanisms. You can see in this figure, for the task forwarding manipulation attack on swarm formation tasks, normally the robots can form the correct structure very quickly with the presence of one idle robot. The workload can still be completed, but with the attack, one present adversary robot, this workload cannot be successfully executed, and the formation similarity is very, very low. So in the end, we want to discuss a little bit on the possible defense over the different threats in the MRS workloads. Consider a simple case where a robot report its position at T1, which has P1, T1, and another position at P2 at T2. We can actually have two ideas to measure if these data are real or not. Firstly, we can have a rule-based method. For example, we can calculate the distance between these two positions and the time differentiation. And then we can see if the speed of the robot is more than the maximum designed velocity. If that's the case, we can see that the message may contain some malicious information, or at least not real in this case. However, this kind of rule-based method can be easily bypassed because we can see that the adversary robot can actually know the rule-based methods and design some attacks that can just bypass those defense mechanisms. So another consideration is that these rule-based methods should be very precisely designed, which may contain many information that cause system performance overhead on robotic systems where the computational resource is very limited. So the second idea is to cross-validate the data received from different robots, which is a very common solution in the Byzantine problems. The idea is that once we receive the data from one robot, we will let some other robots, which is near this robot, and use their sensor data to validate if the data from this robot is correct or not. However, this requires the robot to stay together and validate the result from each other, which is against the original design purpose. That is to maximize the system performance. Because once you let the robot aggregate together, the performance is not maximized. So in multi-robot system design, there will always be this performance versus security issue that we need to balance and consider. In the future, we will try to work on this topic and propose some defense mechanisms to prevent the system from Byzantine threats. Thank you. Then that's all for this presentation. Here are some appendix for the figures in this presentation. Thank you.